And here we are on page 6, and we're going to work through conformational analysis of cis and trans 1-tert-butyl 3-methyl cyclohexane. We're going to draw the skeletal structures and 2 conformations of each, but first we're going to draw cis 1-tert-butyl 3-methyl cyclohexane in its 2-dimensional form. 1-tert-butyl to 3-methyl. We add in the remaining groups like this. Over here, I highlighted to help you guys out that this is carbon 1. We know that since the bonds in the ring are going down, then the axial group must be pointing up, and the hydrogen, or rather the equatorial group, must be pointing down. The tert-butyl group is up here, and this is sort of defined by this group being up and that group being up, meaning they're coming towards you. So when you turn the chair on its side, this is pointing up. On this particular chain conformation, this group is up and axial. And we're just going to erase that stuff there. On carbon 3, we should have another methyl group, and this methyl group is pointing up, the CH3 group here, and it is up and axial. And we know that because the 2 bonds in the chair are going down, so the axial must be pointing up. The equatorial substituent is pointing down, as we'll see in the next example. We have the tert-butyl group participating in a ring flip. And remember, a ring flip is when the head of the chair becomes the ottoman. So this is now an ottoman. And then the ottoman of the chair becomes the head. So this is carbon 1 all the way on the right on both structures. We have this group here, the tert-butyl group should still be up. It's going to become equatorial now. It does a little bond rotation. And here we have it. The hydrogen, if you choose to draw it, is pointing down, but that's not necessary, so I'll take that out for simplicity. And then over here is carbon 3. And carbon 3, once again, is that methyl group. We can do a better job than that. And the methyl group this time is also up and equatorial. So we're going to compare the relative stabilities of each. This one has 2 equatorial substituents. And we see that there is no diaxial strain associated with this molecule. Whereas the other compound has 2 axial substituents, and these 2 axial substituents are participating in 1,3 diaxial interactions, or in other words, they bump into each other. And we also have diaxial interactions between the tert-butyl group and the hydrogen, and between that hydrogen and the methyl. So you have significantly more, or in this case, some, or let's say lots of diaxial interactions. Remember, these are specifically 1,3 diaxial interactions that cause greater strain. So this is going to be a less stable conformation, and this is going to be more stable. 1,3, once again, is the relative position between the 2 substituents, or the 2 groups that are axial on the same side. So hydrogen, once again, participates in a 1,3 diaxial relationship. This is a 1,3 diaxial, and this is 1,3 diaxial as well. The next one, totally separate problem. We have trans 1-tert-butyl 3-methyl cyclohexane, and I'm going to keep the tert-butyl group still pointing up, and now I'm going to make the methyl group pointing down. The first thing we need to do before anything else is make sure we draw a really nice chair. These guys should all be at angles. Okay, so that's 1. And there's the other. That's not my best chair. Let's try that again. So the tutorial in the book has you do 2 parallel offset lines. Have this one out here to the side. Have this one out here to the side. And that's a little bit of a better-ish chair. Sure. So let's add in these groups. This is still going to be carbon 1. I just drew the same chair again. That's awesome. This is still carbon 1. We're going to put the terbutyl group same place that it was above, because that guy hasn't changed, up in axial. Here, up and equatorial. And if you're wondering where the up comes from, there's a plane defined by this carbon here, and we're above that plane on both of them. The methyl group is going to be on carbon 3, 2 carbons away in that direction, but it's going to be down. Now, before we saw this group was up and axial, so down here it must be down and equatorial. Over here, we want it to still be down, 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 equatorial. Here we still want it to be down, but if we do our ring flip properly, then it should be down and axial. So now we compare stabilities. They both have 1,3 diaxial interactions. One has significantly more, and that's the one with the bigger group. This tertiary butyl group here is much larger. It's going to cause more strain, and I already have 1,3 diaxial interactions written up above, so I'm not going to write that again. And then this one is going to cause strain, but because the methyl group is smaller, it's going to be much less than the tertiary butyl group will cause. So altogether, more stable conformation on the right and less stable conformation on the left. Okay, remember, you're not asked to compare whether cis or trans is more stable in this case. It's just these two of the cis and then those two of the trans. Next, we're going to consider the rotation around the C3-C4 bond, and that's highlighted here. We're going to draw the least and most stable conformations using Newman projections. We're going to give a little explanation of the stabilities of each one. So a Newman projection should always be the circle line dot thingy, like this. The front carbon in this case is going to represent 1, 2, 3, 4. So this here is going to represent carbon 3, and then the big circle is going to represent carbon 4. We're going to start with a staggered projection just because I want to stagger. And on carbon 3 here, we have a hydrogen, and then that whole terbutyl group, including carbons 2 and 1. I'm just going to put the tertiary butyl group up here just because we can put it pretty much anywhere we want, just as long as the other two are hydrogens. The one in the back, carbon 4, has 2 hydrogens and a chlorine. In order to draw what I'm trying to get to be the most stable conformation, you want the largest groups farthest away from each other. And I hope we can all agree that chlorine is a much larger group than a tertiary butyl group. These 2 hydrogens we have out of the way. Okay, so again, we want the largest groups away from each other. This is going to avoid gauche interactions. All right, so all staggered projections, any more stable conformation of one of these would have to be in a staggered conformation, but we still want to avoid gauche interactions. And just to give like a quick little swap of what I mean by that, if we were to place these guys in a different position, put the chlorine here and the hydrogen there, still a staggered conformation. It's no longer more stable, but this would be an example of a gauche interaction. So that's what, once again, what we want to try and avoid. Okay, so that is the most stable conformation. The less stable conformation is definitely going to be an eclipsed one. So that's 3, that's 4 in the back. We're going to show that these lines are right next to each other, so the groups are bumping into each other. Once again, this is going to be an eclipsing conformation or eclipsed, and we're going to do our best to try and draw the least stable conformation. I'm going to keep the front carbon stuff the same, still a tertial group, hydrogens in the back. And then on the purple team, we'll have the two largest groups closest together. That is going to cause the largest amount of strain. Okay, so again, the largest groups are close. And more specifically, they are causing torsional strain. Torsional strain is a specific type of steric strain associated with eclipsed conformations. These groups are close enough to bump into each other. There's also hydrogen-hydrogen eclipsing interactions on both of those there. We don't have any Gauss interactions between these two groups or between these two groups. There's pretty much no strain associated with this particular staggered conformation. And there's a lot of strain associated with this conformation. So that's it. That's the exam. I'll do my best to put together some stuff on the pyridine problem, resonance. That'll probably come out in a couple of days. Have a good weekend and take it easy.